Hey everyone, and welcome back. Have you ever stopped to think about what's actually happening every time you walk, wave, or even just nod your head? Well, you're using this incredible, kind of hidden system of engineering. Today, we're going to pull back the curtain and explore the amazing architecture of your body's joints. You can think of your skeleton as the frame of a building. And if that's the case, your joints are all the crucial hardware. They're the hinges, the shock absorbers, and all the connectors that hold it together. And okay, while they aren't literally metal hinges like this picture really gets the core idea across, right? So in this explainer, we're going to take a tour of this internal blueprint. We'll kick things off with what joints even are. Then we'll explore the three main structural types: the unmoving fibrous joints, the slightly flexible cartilaginous joints, and finally, the real superstars of movement, the synovial joints. Okay, let's start with the most basic question of all. What exactly is a joint? And why should we even care? What fundamental purpose does it serve in our bodies? A joint is pretty simply just the place where two or more bones meet. But here's the brilliant part, the part that's so cool. They have two jobs that sound like complete opposites. First, they give our rigid skeleton the ability to move, and second, they hold that exact same skeleton together. It's this incredible balance between movement and stability that is just so fascinating. To really get a handle on them, we can classify joints in two main ways. We can look at them functionally, which is all about how much they move, from totally immovable to completely free moving. Or we can look at them structurally, which is based on what they're actually made of. For our tour today, we're really going to focus on that structural classification, mostly because what a joint is made of directly tells you what it can do. Let's start with our first category, fibrous joints. And here's the key idea to keep in your head for this section. Sometimes, a joint's most important job is to not move at all. So these joints are defined by three key things. First, the bones are connected by this really tough, dense, fibrous tissue. Second, there's no fluid-filled space or cavity between them. And because of that, most of them are what we call synarthrotic, which is just the fancy scientific term for immovable. Let's take a look at the three types. First up are sutures, and these guys are found only in one place, your skull. See those wavy interlocking lines? That's where the bones of the skull have literally fused together with super short connective tissue fibers. This design is all about providing incredible strength and protection for, you guessed it, your brain. Next, we have syndesmoses. Here, the bones are connected just by ligaments. But because these fibrous bands are longer than the ones in the sutures we just saw, they allow for a little more give, a little bit of movement. The joint between your tibia and fibula way down near your ankle is a perfect example of this. And the last type of fibrous joint is a really specialized one called a gomphosis. It's a peg and socket joint, and you only have them in one place, holding your teeth firmly in your jaw. The periodontal ligament is that fibrous tissue that anchors the tooth, making it incredibly strong and, yeah, immovable. Okay, so we've gone from the immovable to what I like to call the middle ground. Let's look at cartilaginous joints, which offer this brilliant compromise between being rock-solid stable and having totally free movement. Just like the name suggests, in these joints, the bones are united by cartilage. And just like the fibrous joints we just talked about, they don't have a joint cavity. But the big difference is that most of them are ampiarthrotic, which means they're slightly movable. Now, our first type, synarthroses, is a bit of an exception to that slightly movable rule. They're actually immovable or synarthrotic. A great example is the joint between your very first rib and your sternum, where a solid bar of hyaline cartilage just locks them together. The second type, symphyses. These are the true, slightly movable joints of this whole category. Here, the bones are covered in hyaline cartilage, which is then fused to this tough pad of fibrocartilage. This setup makes them strong, amazing shock absorbers, and flexible. Think of the discs between your vertebrae or the joint in your pelvis. And now it's time for the grand finale. Let's talk about the joints that get all the attention because they allow for all the big, sweeping movements we make every single day. I'm talking about these synovial joints. The one crucial feature that separates synovial joints from all the others is right there, smack in the middle of this diagram, the joint cavity. This is a space between the bones that's filled with a lubricating synovial fluid, and that fluid is what allows them to be diarthrotic, or in other words, freely movable. It takes a really complex system to allow for so much movement. All synovial joints share 6 key features: smooth articular cartilage on the ends of the bones to cut down on friction, the fluid-filled joint cavity we just mentioned, which is enclosed by a tough articular capsule, the synovial fluid inside that provides lubrication, strong reinforcing ligaments for stability, and finally, a rich supply of nerves and blood vessels. It is a truly elegant piece of engineering. So there are 6 different types of synovial joints, and their classification is all based on the shape of the bone surfaces, because that shape dictates the kind of movement they allow. So let's take a quick tour, and as we go, try to picture where you can find these in your own body. First up are plane joints, where you have flat surfaces that simply glide past each other. This allows for these short little slipping movements, which you can see happening between the small carpal bones in your wrist. Next, we have hinge joints. These are mechanically pretty simple, but they are so important. They work, well, exactly like a door hinge, allowing movement back and forth in only one direction. Just think of your elbow or your knee. Pivot joints. These allow for rotation around a central axis. The joint between the top 2 vertebrae in your neck is a perfect example. That's what lets you shake your head no. Then there's the saddle joint, which is just a marvel of evolution. Each bone surface has both a concave and a convex area, kind of like a rider sitting in a saddle. This unique shape, found at the base of your thumb, is what allows for that opposable movement that lets us grip things. Condyloid joints are kind of like shallow ball and sockets. They allow movement in 2 directions, which you can feel on your knuckles when you both bend your finger and then wiggle it from side to side. Finally, we have the undisputed champion of mobility, the ball and socket joint. Here, the round head of one bone fits into a cup-like socket of another. This design, found in your shoulder and your hip, is the only one that allows for movement in all directions, giving us the greatest range of motion in the entire body. So there you have it, from the immovable sutures in your skull all the way to the freely moving ball and socket in your shoulder. You've just taken a tour of the incredible engineering that lets you both stand strong and move freely. Which leaves us with a question to chew on. Now that you've seen the blueprint, which of these joints do you find the most impressive?